So we're still focused on measures of reliability. So internal consistency is a measure of how well items hang together. So we already kind of talked about how we can look at reliability looking at two forms and correlating them. When we're looking at internal consistency, we're asking more specifically, how does every single item relate to every other item? Again, if we've created a measure and that measure is meant to measure a single construct or concept, we'd expect the items to be relatively connected to each other, related to each other. So are items within the test consistent with each other? One of the ways we can do this is a split half, so we can divide the test randomly into half, or basically odds or even, and compare one half to the items to the other. So that's a simple thing we can do with a correlation. This is often referred to as an odds or even comparison. So we basically take a test, for example, if we have a 20 item test of extroversion, we take the odd items and then correlate them with the even items, and we'd expect to find a strong level of reliability. So that's one of the first ways we can look at internal consistency. However, generally, we're going to go forward with a more advanced technique to look at this. So once we have internal consistency, we can also use the Spearman-Brown formula to allow a test taker to basically estimate the internal consistency reliability of a correlation of two halves of the test. So basically what this allows us to do is, if we have an internal correlation, we can actually start estimating how a test would perform with more or less questions. So in this case, we have a fairly scary looking equation here, but it's very, very simple. The first is n. So n is the proportion of the new test. So if we wanted to actually calculate what would the reliability be with twice the number of items, in other words, double the length, we'd have a 2 times 2. If we wanted to look at half the length, it'd be 0.5. If we wanted to look at 4 times as long, it'd be a 4. If we wanted to look at a quarter as long, it'd be 0.25. And then finally, we're basically going to have to also know the actual reliability of the current test. Now, the Spearman-Brown is something we can easily do, and one of the reasons that this is another statistic that I want you to actually know how to calculate is that it is a useful tool if you've created a measure. For example, let's say you have a 5-item measure of extroversion. You've done your reliability analysis, you have an internal consistency, and the internal consistency is a little bit low, 0.7. You can actually, before you actually start developing more items, do a quick estimate of, is it worth your time? In other words, based on this reliability, what would happen if you actually created 5 more good items? You double the length of the test. You can actually kind of get an idea of what that relationship would be. And we're going to talk about basically what those scores for internal consistency need to be. Generally, we often use a scale of 0.7, 0.8, or 0.9. So if you're below 0.7, that test is not very internally consistent. So the question becomes, what if I double the number of items? Can I get to at least a 0.7? A lot of times, if we're truly using a test to actually make decisions with, we want that internal correlation to be 0.9. So you might even have a fairly reliable test at 0.85, but you're still thinking of, like, I want to get it to 0.8, 0.9. What do I have to do? How many items would I have to add? Now, again, it's not just 7 items and you're going to be there. This is an estimate based on similar items that are also highly correlated. The other advantage of the Spearman-Brown formula is, as we talk about some more advanced ways to look at internal consistency, a lot of those techniques are also going to use the Spearman-Brown formula to ask the question, what happens if we remove or add items? So let's briefly go over how we'd use this equation. So again, if, for example, I had a reliability of 0.80, a fairly reliable test based on that 0.7, 0.8, 0.9, but maybe not quite as long. But in this case, I'm actually okay with a 0.8. In fact, I'm even okay a little bit lower. And I'm asking the question, what if I actually cut this test in half? So instead of, for example, 20 items, I took it down to 10. Would I still have decent reliability? So the two numbers we need to run this equation are reliability, in this case 0.8, and again, the ratio of the test, half as long, 0.50. So I'm just going to plug those numbers into this equation. So at the top of the equation, I have n, which is the number, the new test length, by reliability, so 0.5 times 0.8. The bottom is 1 plus n minus 1 multiplied by reliability. So again, 1 plus 0.5 minus 1 times 0.8. I'm now going to just do the math. So at the top of the equation, it becomes 0.40. At the bottom of the equation, we're going to look at negative 0.50 minus 1 in the first parentheses. That's going to become negative 0.40. 0.50. We're now going to multiply those. We multiply them and it's 1 plus negative 0.40, and that's at the bottom of the equation. And again, we're going to actually do that, and it's going to be 0.6. And the new reliability then is going to be 0.4 divided by 0.6, which is of course 66.6, or basically, I'm just avoiding actually calling it the number of the beast 666 here. It's 0.666 on agnosium. You could round this to 0.667. That tells me that if I cut the test in half, it's actually going to be below 0.7. I probably don't want to do that. I might want to now look at what if I take it down to 0.75. In other words, I get rid of 25% of the questions. I'm probably going to find it's going to actually have a reliability closer to a little bit over 0.70, and that's going to give me some information of how I can adjust this test. If we're doing internal consistency on basically dichotomous outcomes, so for example, true and false questions, there's two different formulas that we can use, and these can be found in almost every statistic package, including SPSS. We're not going to hand calculate these. The first one is the Kuder-Richardson 2-0, and the second one is the Kuder-Richardson 21. The 20 is used for outcomes when the item difficulties vary for each item. In other words, there's some easy true and false items, there's some hard ones. The 21 is actually it's a more reliable test, but it also has an assumption that all of the item difficulties are the same. So we'd actually have to run item difficulties to find out how often are people getting these items right. If we found we had 20 true and false items and all of them are approximately 0.8 in difficulty, in other words, about 80% of the people are getting them right across the board, we could run the KR21. If we find that there are some items that less than 20% of the people get, there's some items that 50% of the people get, and there's some items that 80% of the people get, we'd probably have to run the Kuder-Richardson 20 instead. But for most cases, when we're measuring psychological constructs, we're going to have continuous data. So we're going to have a set of items that are all measuring things on using continuous data. Again, thinking back to the lecture last week where we were talking about different types of data. In that case, what we're actually going to be using is Combrach's coefficient alpha. So it's fairly similar to a correlation, but Combrach's alpha is actually looking at the mean of all possible split half correlations corrected by Spearman-Brown for what if we remove that item. So I have the equation here, but we're not going to actually hand calculate this directly, but it is a good idea to have an idea of what's going on here. K is the number of items. So we're starting with the number of items divided by the number of items minus 1. And then we're multiplying the variance for each and every item. So we're basically calculating the variance of every single item. We're squaring that variance, and we're adding it all together. We're then dividing it by the variance of the total score of the tests. So each item's variance divided by the total variance, again, minus 1. So you could hand calculate this, but it actually gets fairly obnoxious, honestly, with most tests because there's a lot that we have to calculate. And again, most statistical packages will run an alpha for us. So we're more interested in how we interpret that alpha and how we understand that alpha. So generally what we're going to be doing is we're looking at the average items of correlation. So for example, if we're looking at item 1 versus item 1 across 50 people that took the test. In that case, that item might actually have, so the item by the item is going to be 100%. It always correlates with itself. But how does that item correlate with the second item, the third item, the fourth item, the fifth item, the sixth item? We're averaging this. And again, if it's a highly reliable test, all of the items are measuring a similar construct. Now, it doesn't tell us if it's a valid construct. It's simply telling us that it reliably measures a construct, something. There's one underlying thing that this measure is measuring. That's what that final score is going to give us, that 0.85 in this case, but generally, again, on that 0.7, 0.8, 0.9 scale. So we can also use Combrach's alpha to detect good and bad items. We can find items that don't correlate with others. And one of the functions of actually most of the statistical packages like SPSS out there is it'll also tell us for each and every item whether or not the scale's total Combrach's alpha would get better or worse if it's removed. So reliability can often be increased by preserving the items that are most consistent with each other and removing items that are least consistent. And SPSS will provide us statistics that indicate how reliable it can be with improvement as each item is deleted. Now note, as we're removing items, we're also making the test overall less reliable. Less items generally means a smaller score because we have less items that are actually getting at the score. But in some cases, the items are so poor at measuring the construct, they need to be removed. So we're looking for items that, if deleted, would increase the alpha. And there's a little bit of art to this. So for example, we might have a Combrex alpha of 0.89, and we have an item that basically would improve it. So it goes from 0.89 to 0.90 if we remove that item. It's a minorly bad item. We might look at that item though and go, you know what? That item really is an important item that is a part of this construct. I'm going to leave that in. However, if we saw an item that basically, again, the overall measure is 0.89, and if we remove that item, it jumps up to 0.97, and we looked at that item, and the item is like, I can see what's going on here. This really isn't a great item. It's not a great measure of what's going on, and I can see how people might be misreading this item. So we obviously want to be thinking about items as we write them. We want to make sure that they're capturing that construct definition that we're after, that each item is kind of crafted around the construct that we're measuring. But at the same time, this is a statistical way we can find if an item actually is failing to do the job. But neither should be the end-all decision maker. We shouldn't decide to remove an item simply because we don't think it's a great item necessarily, and we shouldn't remove an item simply because it might cause a slight increase in reliability. We want to combine the two to make these decisions. So what is good reliability? I've already kind of talked about this, but Nunley suggested that basically zero point 0.7 is acceptable in most cases, 0.8 is good for most cases, and 0.9 is necessary for clinical decision making. So if you've got an assessment that you're using to decide if someone gets hired, if you have an assessment that's being used to determine if someone gets promoted, if you have an assessment that determines if someone is going to be diagnosed with a clinical disorder, you want to make sure the reliability is that 0.9 or higher. Generally, considering 0.7 is okay, 0.8 is good for research, 0.9 is good for decision making. So if you've got a scale that's 0.7 or higher, between 0.7 and 0.8, that doesn't mean you necessarily want to throw it out. In fact, some of the psychological measures that we're fairly used to live in this range. Specifically, for example, if we think about the ambivalent sexism scale, it often has reliabilities in the upper 0.7, 0.78, 0.79. And when you look at the items, though, you could make a better scale, but you're going to start getting away from items that need to be in there to really measure this idea of ambivalent sexism, for example. So, for the most part, the science of psychology has accepted that as an acceptable scale for most uses. However, I wouldn't want to use that scale to determine who gets sexual harassment training. I wouldn't want to make a decision on it. I would want to use it more as a diagnostic tool to start conversations. And again, when we're doing a reliability estimate, recognize that if it is zero point 0.9, that still means that approximately 10%, actually almost 19%, because again, remember the effect size, the percentage is R squared. So zero point 0.9 times zero point 0.9 is 0.81. So actually 19% of the variance is actually coming from somewhere else. It's not the true measure of the scale. It might be error due to the construct. It might be error to the administration. It might be unidentified error. It might be the scorer themselves messing things up or the scoring sheet. But again, we want to reduce that error as much as possible. And that's really the goal of measurements of reliability. So knowing that every scale, every measure that we take has error in it, that there is no way to completely get rid of that error, that no matter how reliable a test is, there's still going to be some error. One of the things we might want to calculate is actually a measure of that error. And this is often referred to as SEM, or standard error of the measurement. It basically looks at a sample of means and estimates the group scores, with each sample mean having a certain margin of error known as the standard error of the mean. So we're basically estimating first how much error is there around the average score. Then we're looking at observed scores to estimate what is the plus or minus score or likelihood of that person's score actually going there. So what I'm thinking about this way, conceptually, remember that equation that true score equals observation plus error. Observation is the score. So someone is given a measure of sexism on a 1 to 5 scale, 1 being not sexist, 5 being highly sexist. They get a score of 4.25. What's the chances of that 4.25 actually being accurate? In other words, we know that's the observation, but we also know there's error. If we can estimate the error, we can actually provide an SEM along with that score. So for example, this person has a 4.25 score, but we're pretty sure that their range based on that is plus or minus within half a point. In other words, between 4 and 5. If our measure was more reliable, that standard error might be smaller. It might be their score is 4.5, and we're pretty sure it's between a 4.25 and a 4.75. If the reliability of the measure is actually lower, it might be even greater. It's anywhere between a 3 and a 5, for instance. So this is giving us the ability to put a numerical value on an estimate of our error. So as sample means and standard errors of the mean represent the range of population means, observed scores and standard error of measure represents the range of scores. That's a really complex way to say we're basically just trying to estimate the amount of error that's left in the scale and provide decision makers with that information. A lot of times we will see SEMs being presented with testing scores when people are actually applying for a job. And it's basically to get a range. So some companies may actually use this as a way to make sure that they're making diverse hires as well. Instead of taking the absolute highest score, they look at everyone that scored within a range of the standard error measure towards the top, and then they actually look at them as individuals. So let's talk about how we actually calculate this, and we'll walk through this calculation as well. So the standard error of the measurement is the expected variation in scores. So again, we've got the sigma there, which represents the standard deviation for this particular sample, and R represents the reliability of the measure. Confidence intervals provide a range of plausible scores with a 95% confidence. In other words, we're 95% sure that someone's score is going to fit within their score plus or minus the confidence interval. And the confidence interval is simply the observed score plus or minus the SEM times 1.96. So remember, 0.196 is an important number. It represents plus or minus on a standard distribution, 95% of scores are going to range within that. So we're basically calculating off the observed score plus or minus 95%, where does that score actually range? And obviously, the more reliable test, the smaller this number is going to be. The less reliable the test, the larger this number is going to be. So again, we're going to go through an example where we actually calculate this. So we have an example here where, again, we first need to calculate the standard error of the measurement. So in this case, we know the standard deviation from the test is 0.75 and the reliability was 0.80. So we just plug those numbers in. Again, we have 0.75 times the square root of 1 minus reliability, 0.80. So 1 minus 0.80 is 0.20. We then take the square root of that, which is 0.45. We then multiply 0.75 by 0.45. We get a standard error of the measurement of 0.34. We're now going to multiply that by 0.196, and we get 0.67. That means whatever anyone on this particular measure in this particular sample, anyone's observed score, we're 95% that they're certain that their observed score lies plus or minus 0.67 from what that score is. So if someone has a 5, we would say that we are 95% certain their actual score is between a 4.33 and a 5.67. So again, what we're really looking at here is the different ways that we can use reliability. We can use reliability to look for the relationship between two measures over a period of time. We can use reliability in different ways to look at different raters. We can use reliability to look at whether different forms measure the same thing. And finally, we can use Conbrax alpha to get a really good measure of the overall reliability of a series of items that are measuring one construct, including information about potentially poor items. Once we have that Conbrax alpha, we can then use it to actually calculate how accurate the test is based on the confidence interval based on the SEM. So again, SEM is a statistical term. It's based on the standard error of the measurement, and it's simply coming from reliability and standard deviation. And then the confidence interval is basically the plus or minus estimate of error based around any observed score that we find on that test. So again, I strongly encourage you to read the textbook chapter that goes along with these lectures to really get a feel for this reliability. I've kind of gone over broadly what reliability is, the ways we use it, and some of the statistical techniques we use. Some of them we talked about at a high level because we typically use statistical programs, but some of them we actually got into the weeds of how we calculate them because they're fairly simple. And there are also tools that we can use to look at reliability and also how we present those scores. For example, the confidence intervals and how we're presenting those scores to people, acknowledging that there's error in our measurements.